This is after lunch already. So I should remind people what underspread means. What does underspread mean? Good. I hear some noise and I decode whatever I want to decode. And underspread means that the channel coherence time is much longer than the delay spread. Okay? All right, let me remind, this is important because that's the key reason why OFDM works. Okay? All right. So underspread means that the delay spread is much more than the coherence time. Okay? That means the channel can be thought of as a linear time invariant channel over a long time scale before it changes over to another linear time invariant channel. Okay? Now, why is this important? Because we know that for linear time invariant channel, there's a very important property. Okay? The property is that if I send sinusoids, complex sinusoids to be exact, they are eigenfunctions of linear time invariant channel. What does eigenfunction mean? Eigenfunction is really a mathematical way of saying no ISI. Right? Because what does eigenfunction means? It means that if you send that waveform, all you get is a scalar multiplied by that waveform. So in other words, if I modulate my information symbol to that waveform, then I receive a scalar version of that symbol. Another wave symbol modulated on a different sinusoid waveform will not interfere with me. Okay? So therefore, I should really be signaling in the frequency domain and then transform to the time domain. So if I modulate information in the time domain, then output is going to be a function of multiple symbols. But if I send information by modulating into different sinusoids, then because of the eigenfunction property, the output at a particular frequency is going to be only a function of the input at that frequency and not input at other frequency. And so we have removed ISI because ISI means that an output is a function of many symbols. But now we have decomposition. Okay? All right? So that's the idea. The idea is we want signaling in the frequency domain and convert in the time domain. Okay? So let me draw a picture here. Essentially, we want to do something like this. All right? So what do we want to do? We want to send in the frequency domain. So these are my symbols, x1, x2, x3. Okay? Each symbol represents sending on different frequency. Then I want to send in the frequency domain. So what I want is I want to, by the way, can people actually see the screen? Is it clear from the back? Because I did the survey in the other room, and this is a completely independent room. Okay? So I want to go back to the time domain to send it out over the air. So I do an inverse DFT. Okay? Inverse DFT converts signal frequency domain information to time domain information. And now this goes through my channel, my ISI channel. And then at the output, I go back to the frequency domain to get my information out. So I do a DFT here. And out comes the symbol, x1 hat, x2 hat, etc. Okay? So this is the basic architecture of a OFDM system. Signal in the frequency domain, convert in the time domain, send it over the air, go back to the frequency domain, get the information out. Okay? Now, this sounds very good. However, there are some implementation problems. So, true sinusoids, okay, true sinusoids are eigenfunctions. But true sinusoids happen forever. right? They go on forever. But we're human beings. We live in a finite time. So nothing goes forever. So it's only a finite time. So in other words, we have to convert this into a finite block processing. Okay? Now, once you have finite block processing, okay, then you have to worry about the spillover from one block to another block. Because my channel always have memory, right? So therefore, if I send a block here, I am no longer sending pure sinusoid forever. So they're not exactly eigenfunction. And there's some spillover which I have to worry about. So in some sense, you send a block of symbol. The channel has memory, so there's some edge effect here. And if you send the next block, then this edge effect will screw up the pure eigenfunction property. Okay, so I just really cannot send a block and do I have DFT here and like this. Okay, because I have memory in the system, and that will screw up my eigenfunction property. Eigenfunction property only happens for infinite horizon. For finite horizon, there's this problem. Okay, so here's one way to deal with it. How do we deal with that? One approach is I can leave some God time. I can say, you know what, I will lose something, but I'll leave a God time. Okay. I'll leave a God time of time which is equal to my delay spread. So L symbols here. Then there's no interference with the next block, and so I can start again. So I leave a God time L. All right? So this is one way of doing it, but it turns out that a more clever way of doing this is to do something called cyclic prefix. Okay? So it turns out that if I take this symbol, L of them, and I repeat it here, so instead of sending nothing here, I send those L symbols again here, okay? Then everything is nice. Because essentially what you did is you convert convolution into cyclic convolution. So everything becomes perfect, okay? But these are just details, implementation details. But the point I want to say is you have to pay some kind of overhead because you're doing finite processing. The overhead is proportional to your delay spread, L. Okay? So that's the main point I want to emphasize. All right? Okay. So if you look at an OFDM system, a typical OFDM system works like this. As I said, the data, IDFT, you add a cyclic prefix, you go through a channel, you remove the cyclic prefix, you do DFT, and you get back the information. Okay. So at the end of the day, what happens? At the end of the day, we have converted the communication problem in the frequency domain. Okay? So I'm sorry, the notation is not very consistent here, so let me do that. Okay? So now I'm sending data, D1, D2, Dn, C, D0, let's say, and C minus 1. Okay? So this is the data you send. And the output, you get Y1, Y2, tilde, Y and C minus 1, tilde. Okay. And this is at a particular frequency, subcarrier 1, subcarrier 0, subcarrier 1, subcarrier NC minus 1. And at the output, Y0 will be a function of D0 only. In particular, Y0 will be equal to some gain H0 tilde times the data at 0 plus the noise. So if you look at these equations, you will find that there is no intersymbol interference because what you send out at a particular frequency will only appear in that frequency, the output. Okay? So at the end of the day, we have converted a problem into a bunch of parallel subchannels, non-interfering, one for each subcarrier. Can anyone tell me what is the what are these H tilde n? They're the frequency response evaluated at the various frequency. Which frequencies are they? We can calculate that. They are the frequency at, so, okay. Okay. Okay, so this is my baseband representation. Okay, this is the baseband channel. All right. So what I'm doing here is I'm picking the subcarriers, which are essentially uniform space frequency. Okay, and the channel gain of the nth subcarrier is the channel response evaluated at that frequency. Okay, so the number of subcarriers here is n sub c. This is the size of your DFT block. In practice, NC is going to be something to 2 to the power n because you want to do FFT. Okay? All right. So that's the picture. The picture is I pick subcarriers. NC corresponds to NC frequencies uniformly spaced in my bandwidth of interest. The channel gain of the nth subcarrier will be equal to the response evaluated at that frequency for that subcarrier. Okay, so that's the general idea of OFDM. So now, the key question for any OFDM designer, oh, by the way, okay, so how do we do diversity? Okay, so now we should go back to our diversity problem, right? So now we have an infrastructure which converts our channel, our ISI channel, to a non-interfering channel. Okay? If you look at this channel, what does it remind you of? Can we solve? So we're engineers. Engineers are by nature lazy, which means that you should always think, geez, have I solved this problem before? Can I apply some techniques I know already? Have I solved this problem before? Have I seen this problem before? This is exactly, again, the time diversity problem, right? I'm just thinking about time and frequency, subcarrier, interchange. From an information theorist, this is ITA, I guess I can say a few words about information theory. This is so-called parallel channel problem. Time and frequency are all parallel channels. Okay? Yn tilde is equal to Hn tilde times Dn tilde plus Wn. This is the frequency, Hn is the frequency response, but it is analogous to the time response. Different channel at different time. Okay? So now I can apply any time diversity technique to this channel, and I can get diversity this way. Same problem. Okay, so when we apply time diversity technique, one key thing that we mentioned is interleaving. We need to interleave over a time range which is larger than the coherence time, so that we get independence of the channel. Correct? So we have to do interleaving here as well. How many subcarriers? How much do I have to do interleaving? So in other words, if I look at subcarriers that are adjacent to each other, the channel response is very correlated. So therefore, if you code only over a bunch of subcarriers crowded together, then you don't get any frequency diversity, because when this fades, the whole thing fades. No good. You have to code it across further apart frequency. And what's the key parameter here that we should think about? Coherence bandwidth. So now we have to code over subcarriers that are further away than the coherence bandwidth. And that's why these parameters are very important in the design of the systems like this. So you got to think coherence bandwidth is inversely proportional to delay spread. And so that would tell me how much interleaving do I have to do. Okay, good. All right. So let me go on to my last topic, and then we'll take a break. Yes? Okay. So the overhead. Okay. So there's no free lunch. There was a free lunch for me, but I guess there's no free lunch for you guys. Actually, it's not free lunch anyway. I'm working hard here, Alon. The approach is very nice, I think, but there's an overhead. And the overhead is really cyclic prefix. Every block of NC symbols, okay, I have to put an overhead of L, okay? So every block of NC symbol, I have to put a cyclic prefix of length L. This is not information. This is a repetition of information. So this is a waste. It's a waste both in terms of degrees of freedom, and it's a waste in terms of energy. I'm spending energy in sending, no new stuff here. Okay, so I repeat this, and I pay overhead every block. So what's the overhead here? The overhead here is L compared to NC. This is the percentage of overhead. Okay? And that's a key number. You want to keep this number small. And let's get a sense of what constrains this number in terms of the physical parameters of the problem. Okay. Overhead is L divided by the OFDM symbol time. Okay? Cyclic prefix is dictated by the delay spread. Okay, so in an outdoor situation where the delay spread is large, you have to keep a large prefix. In an indoor environment where the delay spread is smaller, you can keep a smaller overhead. Okay, on the other hand, okay? Now, let me think. How about NC? Why? I never talk about NC, right? Why don't we just use like huge NC? Then my overhead becomes insignificant. So what limits the choice of NC? What limits the choice of NC? So remember, NC is the time at which I am doing this OFDM DFT, right? So then the channel has to be time invariant over this time. Otherwise, the sinusoids are not eigenfunctions anymore. So NC is limited by the coherence time of the channel. NC has to be chosen such that a DFT block is much less than the coherence time, so the channel remains constant. You can also make the same statement in a frequency domain. Okay? So I just erased this, but if you look at the frequency domain picture, the number of subcarrier is NC. Okay? As I increase NC, what does that mean? That means I'm putting more and more subcarriers in the same bandwidth, W. Okay? So what limits me from putting a very dense spacing of subcarrier? I'm limited by the fact that there is Doppler spread. Remember that because the channel is time varying, there's a Doppler spread, 50 hertz in an example. Okay? Or 100 hertz. So therefore, this spacing is limited by my Doppler spread. This spacing should be much larger than Doppler spread. Otherwise, these frequencies will start interfering with each other. Intercarrier interference. Okay? This is exactly the same condition as the coherence time. Remember, coherence time is reciprocal of Doppler spread. I'm just giving you a different way of looking at the same phenomenon. Okay? So now, combining the two conclusions, we have what? We have NC is limited by the coherence time. L is limited by the delay spread. If I want to make the overhead small, that means it will only work if the channel is such that the delay spread is much more than the coherence time. Otherwise, I cannot make it work. Fortunately for us, that is true for most wireless channels because wireless channels are underspread. Okay? That's why the underspread definition is important because it enables OFDM. Okay? Just a quick example before we leave. So flash OFDM, this slide is a bit outdated already. Used to be a company called Flareon. Right. A few months ago, it got bought by Qualcomm, so I should really say Qualcomm flash OFDM system. I don't know why. My talks have examples from a lot of systems, but eventually they all got bought by Qualcomm. So it's very strange, but true. It has nothing to do with being in my course, I don't think. Okay. So example, just to give you some numbers. Bandwidth is at 1.25 megahertz, so-called 1x bandwidth. OFDM symbol is 128 samples, so they use 128 FFT. So NC is equal to 128. This is called OFDM symbol. The whole block is called OFDM symbol. Okay, as 128 samples is 100 microsecond. Cyclic prefix, they have 16 samples, 11 microsecond. So the overhead is 11%. Okay, so I pay 11% overhead, and what I get is this lack of ISI. So the receiver and transmitter are now essentially working with a system without ISI. We'll see another advantage later on when we talk about multiple access. Okay. All right. So okay. So that's it for this. So we've covered 3 different approaches to frequency selectivity. Now it's good time to take a break, 10-minute break, and then we move on to the next section. Okay, good.
There are refreshments when you head out the door. They'll be on your right-hand side, and there will be some photos up.
Point-to-point communication, main theme being diversity. So now we're going to move on to talk about system, in particular cellular systems. After I'm finished with this, we'll call it a day. And then tomorrow, I will start revisiting the whole problem again, but from a more information theory point of view. And so tomorrow, we'll go part a bit longer than scheduled, maybe up to about 12:30, if that's okay with people. Because I'd rather go a bit longer tomorrow morning than go till 7 o'clock tonight. And then it'll be me talking to Alon. Alon is like captive audience. Reminds me of a joke my advisor told me. My advisor Gallagher, he said he was chairing a session once, and it was the last session of the last day of the conference, and there were only 2 people in the session, him, the chair, and the speaker. Although he didn't tell me whether he was a speaker or not, so I don't know whether it was 1 person or 2 persons, but at most 2. Okay, so so we talk about systems, and the 2 main concepts I want to bring onto the table right now, when we talk about multiple users, is the issue of multiple access and the issue of interference management. So the general picture is that you have now a network of base stations, okay? And you have multiple users that each base station serves. The problem of multiple access refers to how do you share the resource within the cell among multiple users, okay? Both in terms of the downlink, that is from the base station to the users, and also from the users to the base station uplink. Some people would like to use the word forward link as a synonym for downlink, and reverse link for uplink. I like the word uplink and downlink better because typically base stations are higher up, mobile is on the ground. When you tell me forward link, reverse link, I always ask my friends the question, so reverse link, reverse of what? Now I got confused, so I don't use that. Okay, so multiple access is one issue, and the second issue is inter-cell interference management, okay? So when one starts talking about systems, then you see a sort of a qualitative difference between what we talk about now than what we talked about earlier. Earlier, we try to put everything in terms of equations and talk about those equations and so forth. But once one starts talking about systems, things become quite complicated, and not everything can be expressed in terms of just simple equations. So we sort of bring more engineering insight into the picture. Okay. All right. Some history, like every good thing in engineering and communication, it started off at Bell Labs. Cellular system is, in fact, the concept is introduced at Bell Labs in the 70s. Okay. The first cellular systems are, at least in the United States, are AMPS. Stands for analog something or another. Never quite figure out what it is. It's an analog system in the early 80s. I'm sure the phones must have weighed a ton at that time. And then comes the Europeans with their pan-European wide standard, GSM, okay, in the late 90s. GSM can be thought of as a narrowband system. And then we have the Qualcomm folks came up with this idea of doing wideband CDMA system. The system got standardized in the early 90s, deployed in the mid-90s, okay, IS-95. And then now we're talking about 3G and 4G system. Funny thing is that the 3G system haven't been fully deployed yet, and then now people are talking about 4G already. So it's kind of a shifting target, what these 3G, 4G refers to. So what we're going to do is, in some sense, we're going to, so this is like a law school type of thing. So we study things through case studies, all right? And we're going to go through 4 cases. And using the 4 systems, I want to bring to light the various engineering issues involved in talking about multiple access and interference management. I must have forgotten, but interference management refers to, of course, dealing with interference between different cells. Okay? All right. Okay. So these are the 4 systems I'm going to look at. Very simple system, narrowband GSM system, relatively simple. CDMA, a wideband system. OFDM, another wideband system. And then I'm talking about opportunistic communication tomorrow. Okay, so these are the 4 systems we're going to talk about for the rest of the course. And a GSM system, essentially, what you do is you convert the multiple access and interference management problem, so you're engineering them away into making the problem into a bunch of decoupled point-to-point communication problem. So what GSM does in particular is it takes the whole bandwidth, chop it up into many relatively narrow bands, 200 kilohertz in bandwidth. You chop each of the bandwidth into time slots, and you divide the time slots into 8 for 8 users. Okay? So at the end of the day, what happens is that users in the same cell are orthogonal to each other. Okay? They never interfere with each other because they either occupy different time slots and /or different frequency bands. So orthogonality is maintained. Multiple access is not an issue. Okay? Now, you may have interference between different users in adjacent cells. Okay? That may happen. However, that is typically avoided by doing so-called reduced frequency reuse. Okay? So one attribute of the wireless channel is that wireless strength decreases with distance. That is both a blessing and so if you have a coverage limited issue, then decreasing channel strength is a bad thing because that means you cannot cover your whole area. However, if you have a lot of base stations in your network, then the problem becomes more a problem of interference. And there, reduction in channel strength is a good thing, because now that means if you are sufficiently far away, then you can start reusing the same frequency band for different users. So in GSM, typically you do not reuse the same frequency immediately in the adjacent cell. Okay? So here you chop up into cells, so the numbers refers to the channel, frequency channel, and you typically do not reuse one until you're sufficiently far away, like in this example, 2 cells far away. Okay? And the reason is because you want to minimize the intercell interference. Okay? So at the end of the day, what happens is the following. You keep users orthogonal within the cell. You reduce frequency, you reduce intercell interference by a reduction in frequency reuse. And therefore, each user is operating at relatively high signal to interference and noise ratio regime. So in a point-to-point communication, we often talk about S and R. In a multi-user system, we often talk about SI and R, signal to interference plus noise ratio. Okay? So users operate relatively high signal interference noise ratio because there's very little interference. The price to pay is you essentially loses the degrees of freedom in the first place. So here, in this example, I am reusing the frequency only at 2 bands away. There's a frequency reduction of 1/7. So each cell essentially gets only 1/7 of the bandwidth. Okay, so you start with, say, 20 megahertz bandwidth. You end up only with 2 or 3 megahertz per cell. So you lost a lot of degrees of freedom already, and that's the price to pay. So now we want to revisit the key issue of why I cannot reuse the same band in adjacent cell. If I could, then I have a more spatially efficient system because I'm using more of the bands per cell. And the reason is this picture. Okay? All right? So what's the picture? The picture is the following. Suppose you have 2 users. So you have 2 base stations. Suppose you have 2 users. Okay? This user is talking to this base station. This user is talking to this other base station. Okay? Suppose you have an adjacent cell and you insist on using the same band. Okay, so this guy and this guy is on the same band. All right? Now, what's going to happen is if this guy's going to roam around. This guy will roam around. And it could happen that this guy has a very decent channel to the other cell. And when that happens, you will have very significant interference. Okay? So therefore, you have to always engineer for, in some sense, the worst case or near worst case, when this guy has a very clear signal channel to your base station. And in terms of randomness, that means that the interference is very random. And when you design a system, you have to worry about the near worst case. So you have to be very conservative in allocating resource to this user. And therefore, that's a problem. So the lack of interference averaging is what prevents you to use the same frequency reuse, in adjacent bands. You want to make sure that the worst case is not too bad. All right? And so what you measure, if you measure the receiver, the interference is very random. Okay? So in some sense, whenever you want to move to a system with a better frequency reuse, the key idea is essentially how to have a better, more controlled interference. Okay, so let's immediately move on to that topic. Okay, so we go on to CDMA. So CDMA says, you know what? I don't want to lose 6/7 of my bandwidth. I want every cell, to have the whole bandwidth, to be able to use the whole bandwidth. So that's the key concept of universal frequency reuse. Okay? Universal frequency reuse refers to all the users in all the cells share the same bandwidth. Okay, 1.25 megahertz. So as we said, this maximizes the degree of freedom usage. Now, the key reason why you could do that is because now we have better interference averaging. Okay? So why is that? Because remember, in our spread spectrum system, everybody's signal is spread across the whole bandwidth. Okay? So the interference is now no longer coming from one user, but from many users, each of which has a lower power per hertz, because his power is spread out across the whole bandwidth. That means the interference that this base station C is no longer from one user, but from a multitude of users in the adjacent cell. Okay? So the chance that you get a very bad interference will be the chance that essentially you got a bunch of users, all of which have good channel to your base station. And that's a much smaller probability event. So now, because of averaging, the interference that's created by this cell is now much more manageable compared to the interference created by one user in your narrow band. So this is the basic principle underlying universal frequency reuse. You have interference averaging, and that allows frequency reuse. Okay? And there are several other benefits as well. For example, because everybody is using the whole band, that means what? That means when you go from one cell, drive your car to another cell, when you are somewhere in the middle, where the reception to a base station may not be that great, you have actually another base station also can listen to your signal at the same time, because everyone is using the entire band. So everyone just listens to the signal. And so effectively, you get reception at two antennas, macro diversity, two base stations. And that allows you to have a more reliable handoff. Okay? This cannot be done in a GSM type system because you have different channels. Okay? You have different channel for different users or for different cells. Okay? So when you move from one cell to another cell, you have to switch channel. Okay. Another thing, which is not a performance advantage, but a deployment advantage, is now I don't have to worry about how to do frequency planning. In other words, I don't have to worry about this honeycomb picture. So this honeycomb picture is very nice. It seems that everything is very systematic and so forth. In reality, these cells are no longer just pentagon. They are very strange shaped depending on the environment. And a lot of engineering work, field work, has been done in assigning the different frequencies to different band. And especially when you try to add more base stations in the network, you have to redesign the planning. This is all very labor-intensive affair. And CDMA sort of got rid of that by saying, you know what, everybody is going to use the same band anyway, so there's no frequency reuse planning. Okay? So what's the challenge here? Okay. So the challenge here, number one, and in fact that was the number one problem that people thought CDMA is kind of something that is good to think about but impossible to implement, is the following. And the problem is the following. Remember, all users share the same bandwidth, right? So now, imagine a situation where you have a green user. He happens to be right below the tower. Okay? And you have a red user, which is near the edge of a cell. And both of them are communicating to this base station. Okay? So in a typical wireless environment, this guy could be 40, 50, 60 dB above this guy, the cell edge guy. Okay? We're talking about 4, 5, 6 orders of magnitude larger power. So therefore, if you don't control his power, okay, then his interference will completely swarm this guy. So therefore, you need to do power control. And that was in some sense, the key engineering problem to solve. And this is so-called near-far problem, in the sense that the user closer by is near, and he's creating a lot of interference to the guy which is farther away. Okay? So you've got to do very tight power control. You've got to make sure that you can control its power so that the received power for different users with different channel strengths are all the same. Okay. Another challenge is we talked about earlier already, which is essentially you are in a situation where you have very low signal to interference noise ratio. Your code rate is very low. You spread the signal. Essentially what you see is that your signal is like buried in a huge amount of interference and noise. You need to be able to do smart coding and signal processing to extract that out. Okay? So that's what needs to be done. Okay? All right. So if you think about how one could design the CDMA system, what do one want to do? Well, this is the design goal of the CDMA system. First, we know how to design point-to-point communication systems with white Gaussian noise. But we have interference on top of the white Gaussian noise. So what they want to do, CDMA wants to do, is in some sense to make the interference like white Gaussian noise as much as possible. Whether or not this is a good thing, I'm not saying that. What I'm saying is that that's the design principle of CDMA. Okay? I want to spread each user signal, and it's done using a pseudo-noise sequence. Okay, good. People are not catching it. All right, fine. All right. Okay, good. All right, 2, I want to do tight power control. I mentioned that already. I want to average the interference from outside the cell. Okay. So now, at the end of the day, what happens is that the interference will look very consistent because I've done the averaging from outside the cell. I've done power control within the cell. Power control applies to mobiles within the cell. Interference averaging applies to mobiles outside the cell. Outside the cell, they are only power control to their own base station. They're not power control to this interfered base station. You can't power control to both base stations, obviously. So you rely on averaging. You rely on the fact that they are on another base station means that the received signal strength from this guy is not going to be terribly strong. And so therefore, you can do averaging to mitigate that effect. Because if it's very strong, then you should be talking to this base station, and therefore power control apply to this guy. Okay. Okay, once you've succeeded in doing that, then you can apply point-to-point design for each link. So now we have reduced the communication problem to a point-to-point problem. And now you can apply all the nice things we learned in the last section, all the diversity techniques, and I could try to design a very reliable point-to-point link. Okay, so you think about the general design goal picture. The picture is the following. In the GSM system, I reduced my communication problem to a point-to-point problem by orthogonalizing all users. In a CDMA system, I'm also reducing the communication problem to a bunch of point-to-point problems, but I allow interference, but I do all sorts of things to make the interference as much like Gaussian noise as possible. Okay? So in both cases, I'm trying to reduce it to a bunch of point-to-point problems. When we talk about the opportunistic communication tomorrow, we'll find that that approach is opposite to that. Okay, but that's tomorrow. Let's try to get over today first. Okay. Point-to-point design, we have already talked about that. Let us apply the principle we learned last time in a specific, last section in a specific problem. In a CDMA problem, the name of the game is to get as much diversity as possible. Okay? Time diversity can be obtained by interleaving and convolutional coding. Convolutional coding in IS-95, turbo coding in 1X CDMA 2000 system. Okay. Frequency diversity is obtained by rake combining of the multipath. We talked about the rake already. Okay. In some systems, you can do, in 3G systems, you can do transmit diversity, like Alamudi scheme, for example. So all of this combines to make the link very reliable. Okay. So now, let's talk about the first approach, how to do power control. Okay. Now, power control, okay, refers to the problem of controlling the power such that the received power of all users in the same cell are equal. Green, red guy, receive power the same. Okay? That's a very important function in a CDMA system. And the reason why it's difficult, in fact, there were a lot of people in the early 90s who did not believe that Qualcomm could make the system work because of precisely this power control problem. So you have to realize that in a cellular environment, if you want to cover a geographical area, okay, of say a kilometer square, then because of the path loss effect, users very close and very far away, the channel strength differ by a huge amount. The dynamic range is huge. Okay? This dynamic range is even bigger than the dynamic range due to the multipath fading. So that dynamic range is about 20 dB. This could be easily 50, 60 dB. All right? So you have to do a power control to this dynamic range. Moreover, this could be changing quite rapidly. So, for example, this guy could be shadowed behind a building. So then his received power is not that strong. But then he may emerge from behind a building, and suddenly your received strength is very strong. So therefore, you have to be very careful and track the guys very accurately so that when he emerges, you lower his power immediately. Otherwise, the biggest problem with the CDMA system is that when his received power is not controlled properly, he swarmed the entire cell or entire sector of the cell. So all the users lost communication. And that's not good. Okay? So how do you do power control? So first observation is that IS-95 or all CDMA systems I know of, almost all, are FDD system. Okay. Recap. What does FDD stands for? Frequency division duplex. Frequency division duplex means that the uplink and the downlink bands are typically tens of megahertz apart to avoid a filtering problem. Okay? Therefore, power control is implicitly a way of the transmitter knowing the channel, or at least knowing as much about the channel as possible. Because you have to power control the transmitter to match the channel, to make sure the receive power is not strong. Okay? So because the FDD system does not have channel reciprocity, therefore, you must be able to do some feedback in order to control the power. Okay? So there's a closed loop and there's an open loop part. Okay? So first, open loop means what? Open loop means the following. You are mobile. You measure the signal that you hear from the base station. Okay? From that measurement, you have an idea. Okay, my channel strength is roughly so and so. In other words, I'm either the cell edge, I'm probably roughly the cell edge, or roughly near the base station. So I get a rough idea what the channel is. Because the uplink and downlink have the same path loss, large scale path loss. The small scale, the fluctuation may be different, but the large scale is more or less the same. So that gives you a rough idea of how many dB you should be operating at in the transmit power. So that should be accurate to within maybe 3 to 5 dB. Okay? Now, this open loop sets a reference point. and from this reference point, you can do power control. Okay? How do I do power control? Okay? The power control has to be done with feedback from the base station. Okay? So the base station is listening to all the mobiles currently in the cell. Okay? He wants to keep the receive power of all the mobiles essentially the same. If he finds that a mobile receive power is very high, okay, then it says, no, send 1 bit, please lower your power. You're too strong now. So you basically send this 1 bit up and down feedback in a RS-95 system. This is sent at about 800 hertz. 800 hertz. 1 bit feedback, okay, to up down the power. So we're talking about overhead. Overhead, and here there's another overhead in RS-95 system. You are sending voice at 9.6 kilobits per second, roughly. Power control is at 800 hertz, 1 bit feedback, so 800 bits per second. So you pay an overhead of roughly 10%. 10%. So that's the cost for RS-95 overhead. All communication systems have overhead. This one's overhead is mainly in the power control bits. There's also another issue, okay, which is that when you first power your cell phone, when you first turn your cell phone, okay, the system has no idea of what the right power level you should be transmitting at, because he hasn't been tracking you. You just turn on, or you just start talking, okay. So you have to. The base station will tell you to slowly increase your mobile power, because you don't want to very rapidly increase your power, because then you may be using the wrong power level, too high, and you start swarming everyone. So you've got to slowly power up the mobile, and this introduces some latency. Okay? This latency is of the order of half a second to 1 second in RS-95 system. Okay? So we're talking about overhead and latency, and that's the price to pay in a power control system like RS-95. Okay, so we'll come back to those two issues later on when we talk about OFDM system. Okay, now let's talk about interference averaging with a little bit more detail. So okay, let's write down the first equation in this section. So the center to interference noise ratio is the received power from the user of interest divided by the noise power plus the interference from the k-1 users within the cell. All of them are controlled to a power P, perfect power control, assume, plus a bunch of interference from all the users in adjacent cells. Okay? So in a large system, what is happening here is that each interferer is contributing only a small fraction of the interference, because there are typically a lot of users in each cell. Remember, numbers. I have a bandwidth of 1.25 megahertz. I have a data rate of 9.6 kilobits per second per user. I better be putting a lot of users per cell. Otherwise, I'm not going to make money. to put it bluntly. So typically there may be 30, 40, 50 users in each cell. Each sector, 30 users. Let's say numbers. So you are averaging the interference from about 30 or even more users in the adjacent cell. Okay? So that's where the averaging comes in. Law of large numbers says that each of this interferer is a random variable, because you don't know where the guy is. The guy could be close by your cell or it could be far away. As they roam around the network, is random. If you only have one strong interferer using the whole band, okay, then you sort of have to allow for the worst case when he is strong. And you have to be quite conservative in your use of resource. However, now there are many of them. There are tens of them, all roaming around. If one of them happens to be close by, his interference will be strong. So the I corresponding to that user will be strong. But he's only one of them. And it's a small fraction. And so the sum of I, the total interference, tends to be much more consistent random variable. Okay? Consistent random variable. So actually, this is a good idea. In fact, this is roughly the idea of interference diversity. Okay? So we talk about multipath diversity, where we're getting diversity across different paths of the signal. Here, we're in some sense providing diversity, but diversity against interference. So we don't want to be at the mercy of one strong interferer. We want to make sure that we're hit by many interferers, each of which are contributing a small fraction, so that even if there's one or two strong interferer, he won't or she won't completely, I can't use the S word, he can't completely mess up the system. So Alon has already given me some etiquette lessons over lunch, and I cannot use certain words now. So now I'm going to avoid them. This is San Diego, where freedom of speech is not completely respected. Is that what you're saying? Oh, boy. Okay, so interference diversity. Okay. Soft handoff, I mentioned about that already. Maybe I'll just skip this. The idea is that you can listen to both base stations at the same time, or both base stations can listen to you at the same time, and you get diversity that way. Let me go on to talk about uplink versus downlink, because there are actually significant differences between the uplink and the downlink in the CDMA system. Okay? Let's first talk about the effect of the multipath. So in an uplink system, okay, in an uplink system, users are typically not kept orthogonal. Why? Because it's very hard to synchronize all the users. Okay, so typically users are kind of asynchronous. They send whatever time they want to send. Okay, so they're not really kept orthogonal. In a downlink, however, I am sending information. So let's start thinking about downlink versus uplink. Okay. In a downlink, what am I doing? I have the base station here. I have the mobile here. Okay. I want to send information to all of these users, typically different information. Everybody wants their own, listen to their own conversation. Okay. Now I want to send information, send signal to all these users simultaneously. Okay. So in a downlink, all the signal is prepared at the base station, as opposed to uplink, where every mobile transmits information asynchronously, distributedly. So therefore, in principle, I could make sure that when I send signal, I send it in an orthogonal way. So I can assign orthogonal vectors to each of the users so that they remain orthogonal. So here's the question for you. The important thing is not that they're orthogonal at the transmitter. But the question is, are they orthogonal at each of the receiver? So in other words, when I'm at the receiver and I want to extract my signal, will that be orthogonal to all the other signals? Let's think about it. So let's remember what we learned from the early sections of the course. When I go through this channel, okay, what happens to my signal? faded. People are faded out. Waveforms which are orthogonal, the sinusoids. If I happen to send sinusoids, then they'll be orthogonal. But in general, for example, if I send CDMA signals, which are basically plus or minus 1, there's no guarantee they'll be orthogonal. In fact, they're probably not. Okay, so therefore, even if I spend a lot of effort in making it orthogonal, in fact, CDMA systems do, they send these sequences called Hadamard-Wash sequences, a sequence of plus or minus 1. The output is not orthogonal. Okay? So the output is not orthogonal. In fact, if you look at the output, let's write down some equations here. Since it's Friday late afternoon, we should now write more equations. Let's focus on what this guy receives. If I think of this received signal, then it's just going to be the channel, let's call this channel H, convolved with the information symbol, let's call it X1 for user 1, into some sequence V1 plus X2, V2, and so forth. Okay? So this is the symbol for user 1. This is the spreading sequence I choose for user 1. This is spreading sequence for user 2, etc. Okay? So these guys, V1, may be orthogonal to V2. But if I go through this channel, then what matters is that is the channel convolved with V1? Is the channel convolved with V2? And these don't remain orthogonal. That's the problem. Okay, so now, how do I demodulate? How do I demodulate? So now I'm thinking about the receiver design at the mobile now. One approach is the following. I could say, no problem. I convolve H with V1, and I treat all of the other stuff as just interference. Okay? And I'm going to do a rake combining on this signal. That's what IS-95 does. And that's what you do in the uplink, and that's what you do on the downlink in IS-95. Okay, so now let's think a bit about whether that's a good idea or not. In the uplink, we suggested that the rake filter is pretty good. Why? Because the interference is very large. So you're operating at a very low signal to interference ratio. The intersymbol interference is negligible. Okay? Okay, so let's look at this situation. All right? So in the downlink, we have this channel. Y is equal to channel convolved with the transmitted signal plus noise. Okay? Now, are we still, is this assumption of low SINR necessarily valid in the downlink? So if you look at this situation between the uplink and the downlink, so let's look at the uplink. So this is the downlink. Let's look at the uplink. The uplink, let's call it downlink. The uplink is a bit different because it's a sum of the signal transmitted from many users. Okay? So in the downlink, plus noise. Okay? In the uplink, everybody's signal is going through its own channel. In the downlink, if I focus on the demodulation question, all the signals is going through the same channel, the channel for that particular user. Okay? That means that here, if I focus on one user, he'll basically see a lot of interference from other users. But here, all the stuff is going through one channel. So if you think about the equalization question, then we should not be thinking about equalizing for this signal. We should be more clever and think about equalizing for this signal. Because all the signal is going through one channel. So if we could equalize this channel, then we could recover the signal. And when we choose these waveforms to be orthogonal, then we can immediately pick out my own signal. And the equalization is now important because now the signal to interference noise ratio may be not so bad. Because now the signal noise interference ratio is not counting these interference anymore because I'm thinking this as the aggregate signal, but it's just this term, which could be small. So therefore, in the downlink, equalization may be much more useful than in the uplink because of the physics of the problem. The entire signal is going through one channel. Okay. So equalization could be beneficial because the SNR could be high. You want to think of this aggregate signal as the signal that we want to equalize for, rather than the signal of the user itself. Okay. The second difference between uplink and downlink is the notion of interference averaging. So I have a question for you. Is interference averaging more effective in the uplink or in the downlink, or is there no difference? Let's think about it. In the uplink, what is interference averaging? Okay. So this is the cell, and then there's an adjacent cell. In the uplink, interference averaging is coming from my 30 mobiles in the adjacent cell. They're all sending signal out to its own base station, causing interference to the adjacent base station. And so there's a lot of interference averaging. In the downlink, what happens? Where does the interference come from in the downlink? Base stations. So if you look at this mobile user, his interference is coming from this base station, maybe another base station. So the interference is coming from a few base stations which are close by. The interference averaging is less effective. Okay? So the first point, equalization, suggests that there would be potential benefit. Downlink could be better than uplink. The second point suggests that the downlink could be more problematic than the uplink. So the two links are different. Okay. So let's move on. So we talk about CDMA. And let's think about what are the fundamental issues, problems with CDMA. Okay. First observation is that in-cell interference reduces capacity. Okay? Why? Because the performance is a function of the signal to interference ratio. Interference is coming from not only outside the cell but also within the cell because everybody is spreading the signal across the whole band. In-cell capacity interference reduces capacity. Okay? Number two, power control is expensive. Okay? Because of the in-cell interference, not only cuts down the capacity, I need to worry about the near-far problem. And I need to send this 800 hertz signal, power control, to regulate the power. And that costs me 800 bits. Okay? So, now, this 800 bits, okay, is that expensive or not expensive? Well, it depends. It depends on the application. If your application is voice, then you send your voice consistently, and you send this 800 bits consistently, and that's a fixed amount of overhead. Okay? However, if you are designing this for a data system, where your data may be very low duty cycle, okay, then the power control could be quite expensive. Why? Because you may not be always sending. And when you're not sending, and when you're still power controlling the user, then you're paying overhead, where the overhead is a numerator, and the denominator is 0. So as we know, if we divide something by 0, it's not good. Okay? So therefore, it depends on your traffic pattern. Okay? So I want to argue that the goal of CDMA is really to do universal frequency reuse. That is, so the logic is a bit strange here. Strange is also an S word, by the way. So Alon does not allow me to use S words. So strange is an S word, though. So let's step back at what we're trying to do here. We try to do universal frequency reuse. Okay? Universal frequency reuse, is that a intra-cell issue or is it an inter-cell issue? Inter-cell issue, right? It's an issue about how do I do resource allocation across different cells of my network. But in-cell interference is a intra-cell issue. So why am I coupling the two issues together? There's no point in forcing myself to do in-cell interference just because I want to do universal frequency reuse across different cells. It doesn't really make complete logical sense. It's only this particular method of CDMA that has these two things coupled together. I could decouple them. And that's what OFDM does. OFDM gives me the infrastructure to decouple the two problems, to allow me to do universal frequency reuse and to keep users orthogonal within the cell. Let's see how we can do that. Okay? So, OFDM. All right, let's think about OFDM. All right, don't worry, guys. I'll finish in 15 minutes here. I hope not everyone will leave by then. No. Oops. Do we have him on videotape? Okay. Okay. So OFDM, how do you think about OFDM? The way to think about OFDM is a grid where in one axis I have the subcarrier. In the other axis, I have OFDM symbols. Okay? And now I draw this grid with columns reflecting the different OFDM symbols, symbol time. This is the first OFDM symbol. Do you remember the size of OFDM symbol is the number, is NC, the number of subcarriers. So I'm mapping my information to a OFDM symbol, and I have different subcarrier and different OFDM symbol. So this is a grid. OFDM presents this grid, and I can imagine I put an information symbol on each of this square, reflecting that I want to send a particular symbol on a particular time on a particular subcarrier. And the good thing is that if the channel is underspread, then things remain orthogonal. So that's how we use OFDM as a point-to-point communication technology to essentially convert the frequency selective channel into a parallel channel where these boxes don't interfere with each other. If I send something here, I receive that thing times the channel plus the noise. And I don't get overspill from one box to another box. Okay? Right? Okay, and the key issue here being that the frequencies, the sinusoids, are eigenfunctions of linear time invariant channel. So the important thing is that it doesn't matter what the linear time invariant channel is. The eigenfunctions are still the sinusoids are still eigenfunctions, orthogonal eigenfunctions. That means I don't have to limit myself to one user using this grid. I could have multiple users all using this grid. So as long as I synchronize all the users to the same grid, everybody do DFT, inverse DFT, then everybody can send on this grid. And provided that different users do not overlap in terms of the grid square, they don't interfere with each other. Okay? So that means if everybody sends sinusoids, then they remain, if they're orthogonal at the transmitter, they remain orthogonal at the receiver. Whether or not it's uplink or downlink, it doesn't matter anymore. In the CDMA, when you send these strange Hadamard wash waveforms, they are orthogonal to the transmitter, but they're no longer orthogonal to the receiver because they're not eigenfunctions. They're just some functions that smart people down the street think about. Okay? All right? But these are very natural functions. They have some physical intrinsic fundamental property because they're sinusoids. Okay. So we're done because now we have a scheme whereby we can use as a multiple access technique to keep users orthogonal. Okay? Moreover, I don't need to do any equalization anymore because there's no intersymbol interference. There's no intersymbol interference. Okay, so that's the picture. So if I do OFDM in a multiple access, so some people like to call this OFDMA, orthogonal frequency division multiple access, then I can have multiple users sharing the same resource but remain orthogonal, whether or not it's uplink or downlink. Okay? So now I maintain orthogonality within the cell. Okay, so let me say a few words about that before I move on to talk about interference management. Okay? So that's the picture. So one way of dividing resource is the following. I have a grid. I assign to each user a unit of resource, which I call in hopping sequence. Okay? So this is a hopping sequence. All right. Somehow they don't look the same. Never mind. Let's go up to there. I don't know why I'm drawing again. It's getting late in the day here. Doing funny things. Okay. This is the hopping sequence. That is, this channel is a measure of resource, and it has the property that it hops through every row and every column of this matrix. Okay? All right? So what's the property here? One is that the different virtual channels never overlap in any of the time frequency slot. Okay? That means these are orthogonal resources. If I assign two different users of these sequences, they don't overlap. They're orthogonal. Two, they hop through all my subcarriers. Why do I want that to happen? Why is that a good thing? Frequency diversity, right? So I get frequency diversity. I maintain orthogonality within the cell. So these are my basic resource, virtual channel. I could assign one of them to a user, two of them to a user, depending on the data rate. Okay? All right. So now I've succeeded in accomplishing goal number one, which is to maintain in-cell orthogonality. But now I want to do out-of-cell interference averaging because I want universal frequency reuse. So I don't want to do frequency reduction in frequency reuse. I want to maintain the CDMA advantage that everybody uses the entire bandwidth. Every cell uses the entire bandwidth. Okay? So now let's think about how to do interference averaging here. Okay? So now we have to be a bit more careful in how we design the hopping sequences in adjacent cells. For example, suppose these are the virtual channels in cell A. Suppose I use exactly the same virtual channel in cell B, adjacent to cell A. Is that a good idea? It's a lazy idea, but is it a good idea? So now I have, say, 5 users in cell A, 5 users in cell B. Now, first of all, there's no way I could invent 5 completely new virtual channels, which are orthogonal to these 5 in the adjacent cell. Because I'm doing universal frequency reuse, right? So every cell I'm using the entire bandwidth. So there's no way I can maintain orthogonality across different cells. I just ran out of resource, right? So they have to be sort of sharing this same grid here. However, I could do things a bit more cleverly in terms of how I assign the virtual channel across adjacent cell. So is it a good idea to use exactly the same virtual channel over and over again in cell A, B, C, D, E? So think about this picture now. Okay? So suppose I have, again, suppose I have two cells, A and B. Okay? Suppose this user is assigned virtual channel 0. Another user is also assigned virtual channel 0. Okay? Is this a good idea? I don't have interference averaging, right? Why? Because when this guy is close to the cell edge or close to this base station, then I will be interfered at by this guy over the entire span of my virtual channel. So even if I do coding across these black spots, coding my information symbol, there's not much I can do because I'll be swarmed every time by this strong guy. Can't do anything. I have no interference diversity. I may have frequency diversity from the physics channel, but I have no interference diversity. In fact, this is exactly, if you use the same channel across the cell, you're exactly back in the narrow band setting. Because narrow band is precisely a special case of this, where each virtual channel is a row, because you're using the same frequency. And so therefore, by nature, the rows are the same. 2 users will have the same row if you assign the same frequency band. Okay? So there's no advantage of this over narrow band communication, which would have problem with doing interference averaging in the first place, if we had exactly the same virtual channel assignments across different cells. So we have to be clever. And one way is to make sure that different adjacent cells have different virtual channel decomposition. Okay, so suppose I assign 5 different virtual channels to cell B. Okay? Now, how much overlap is there going to be between 2 different virtual channels? one from cell A and one from cell B. What's the minimal number of overlap? Well, it cannot really be 0 all the time. What's the minimal number of, if I want to keep every pair, minimize the overlap, what is that minimal number? 1, right? Because together they cover the whole square. Another 5 sequence, together they cover the whole square. So the total number of overlap will be 25. So every pair, the minimal number, is to split this 25 into 1, 1, 1, 1, 1. So therefore, the best situation, and in fact can be done in combinatorics, this is called a Latin square. You can actually choose decompositions such that every pair across adjacent cells overlap in exactly one symbol. And why is that a good thing? That is a good thing because if I am user virtual channel 0 in cell A, and I look at who is interfering with me in cell B, who will be interfering with me? There will be 5 users interfering with me. All the users in adjacent cell will be interfering with me, each interfering with one symbol. If one of them happens to has a clear line of sight to my base station, he will at most erase one of my symbol. And if I code information across these 5, which I'm doing anyway because I'm coding for frequency diversity, then it's okay. I lose 1, I still have the other 4. I can decode. I will only be swamped if every symbol has a very strong interference. But that will only occur, if all 5 interferer is very close to my base station. And that's a very small probability event. So therefore, I've accomplished interference diversity through coding and not through adding in the, not the same as CDMA, but still the same effect. Okay, clever. Okay. All right, so just an example, a lot of these ideas came from essentially Bell Labs. So in the 90s, people like Color Bank, Greg Pawdy, they came up with this idea of this Latin square decomposition OFDM. Aaron Weiner was also involved. And a company was built, the Flarion company, based on these ideas, and acquired by Qualcomm a few months ago, as I said already. Just example, we already saw some of these numbers. Delay spread, 11 microsecond cyclic prefix, overhead 10%. So basically, the basic design concept of the system is the following. It's like going to a buffet. Okay? So you go to a buffet, what do? You pay first, right? So before you do anything, you pay. All right? And what you pay here is the overhead associated with the cyclic prefix, which is 10% in this system, 11%. Once you pay that, you go in, and you are all you can eat. And all you can eat, in this case, is that you have first orthogonality across the subcarrier, so no equalization problem. 2, orthogonality across users within the cell. Okay, so you have all these advantages after you pay that 10% overhead. Okay, so that's the basic principle. Once you pay that overhead, then you are in some sense home free. Okay, I forgot to mention that there's another thing that you need to worry about. Is you have to make sure that the grid, everyone has a common view of this grid. So there must be some synchronization across different users. Okay? And the accuracy of the synchronization, okay? And then you should ask the question, which is how accurate the synchronization has to be. And so you draw the grid again. Okay? All right? So each of these OFDM symbols is, in this example, 0.1 millisecond long. So therefore, everybody should be synchronized to an accuracy which is significantly smaller than 0.1 millisecond. So synchronization should be done at the level of the OFDM symbols, which are very long, compared to the chip, which is of the order of microsecond. One chip is roughly 1 microsecond. Okay, we have a 1.25 megahertz here. So therefore, there are many chips within one symbol. The symbol is huge compared to each chip. So the synchronization is only done at the OFDM level, which is coarser. And so it can be done. It can be done. Okay. So now, let's look at the system advantage of doing this. Okay. So what's the overhead here? The overhead is the cyclic prefix to the OFDM symbol time. Okay? So this overhead is fixed. This overhead is of a different nature than the overhead in a CDMA power control overhead. In a CDMA power control overhead, when you're not sending anything, you may still need to power control that user. Because when he starts sending, you want to make sure that he won't interfere tremendously with the other user. So if the user is bursty, he sends stuff once in a while, then when he's silent, you may still need to power control him. So therefore, the overhead is unlimited. It's not fixed. Whereas here, the overhead is fixed. Is that the total resource you have, 10% of that is paid towards this cyclic prefix. So it's a different nature. And because this overhead is fixed, okay, this allows you to essentially design the system for applications where you have lots of users that are in the system, but only a small number of them actively sending. So now you can keep track of like maybe 100, 150 users, 200 users in the system per cell. Maybe only 30 of them are active at this moment, they're sending. The other guys are all synchronized to the OFDM infrastructure. And whenever they want to send, they can immediately send. Because I don't need to power control them very accurately. Why? Because they're going to send at an orthogonal resource. So they won't interfere with another user. So therefore, as long as they're roughly power controlled, they're OK. I don't need to finely power control them. So I don't need to spend 800 hertz, 800 bits per second to power control all my users. Imagine if you have to do that for a CDMA system with 130 users, just calculate, that will already take up your whole system resource just to power control all these users. Okay? So that's the advantage of having orthogonal resource, is you drastically reduce the power control overhead you need. Okay? So this is useful for a packet system where you have users which are bursty, so they send stuff once in a while, but you want short latency so that when they have stuff to send, they can immediately access the network and send it. Whereas in a CDMA system, if you want to keep a lot of active users, you have to basically turn off the power control for a lot of them. But then when they start sending stuff, when they really want to send stuff, you have to now slowly ramp up the power to make sure that when he sends, he doesn't swamp the whole system. Okay? All right. Okay. So, all right, let me conclude. I think the main point we learned today in the last section is that when we talk about multiple access and interference management, then the important issue that we want to talk about is whether we want to do universal frequency reuse or not. The universal frequency reuse is in general a good thing because we maximize the degree of freedom usage. But to accomplish that, we need to do interference averaging. To accomplish interference averaging, CDMA went the route of everybody sending pseudo-noise signal. Okay? But that causes in-cell interference, and that leads to the problem of power control. In an OFDM system, you maintain this universal frequency reuse property, but you can maintain in-cell orthogonality through this common OFDM infrastructure. And that's a good thing. So you have sort of best of both worlds. Okay? So that's it for today. I'm pretty close to the 4:30 time limit. Yes? And tomorrow, early, I will start introducing information theory into the picture.